Earth, the only planet known to maintain life, a product of scientific phenomena and sheer chance. This blue speck in space holds the past, present, and future of our very existence.
Did you know the ground beneath us is constantly moving, shaping our planet in ways we can't always see? Thanks to Geodetic Time series, we can monitor these invisible changes and predict their impact on our environment and lives. Geodesy is the science of measuring the Earth, including its shape, size, position in space, and how its gravity works. With better technology and more knowledge, this field has expanded to study how the Earth moves and changes, like how the crust shifts, how tides work, and how the poles wobble. Scientists often use data from satellites or instruments on the ground to track these changes. Since the data can be noisy or tricky to interpret, they use careful methods to ensure their findings are accurate and reliable. Environment at geodesy has become important because it looks at how the Earth is changing due to things like climate change. For example, it helps understand how rising temperatures or melting ice affect the planet. This field has grown a lot in the past 20 years because the world needs to understand how our environment is shifting. The articles in this collection focus on new methods and tools to study these changes and learn more about the Earth's movements and climate. Geodesy has its roots in ancient civilizations. For example, in ancient Egypt, surveyors used simple tools like ropes to redraw land boundaries after the Nile River's yearly floods. This practice was crucial for farming and managing land. The Egyptians also applied basic geodesy when building the Great Pyramid of Giza, about 2700 before Christ, using their advanced skills to ensure its perfect square base and alignment with the north-south direction. Similarly, other ancient structures like Stonehenge 2500 before Christ and Roman Empire boundaries relied on early surveying techniques. As time passed, methods of measuring and mapping the Earth improved. Surveyors found ways to make their work more accurate and efficient. However, a major breakthrough came in the 1950s with the invention of electronic distance measurement devices. These tools allowed surveyors to measure distances quickly, replacing older methods that could take days or even weeks. The journal delves into the application of Geodetic Time series in environmental monitoring and earth science, with a focus on advancements in geodetic technologies such as global navigation satellite systems, gravity recovery and climate experiment, interferometric synthetic aperture radar, and terrestrial laser scanning. These technologies are critical for understanding and monitoring Earth's dynamic processes, including geodynamics, climate change, and natural hazards. Geodetic Time Series and Environmental Monitoring. Geodetic Time Series refers to a collection of measurements over time that track changes in Earth's surface and atmosphere. By utilizing data from instruments like GNSS and INSAR, scientists can monitor crustal movements, sea level rise, landslides, and volcanic activity, which are key indicators of Earth's environmental changes. The research highlights small amplitude signals such as seasonal deformations and long-term trends like tectonic shifts that often get overshadowed by noise and complex stochastic processes. Understanding these signals is crucial for disaster risk management, climate change analysis and improving infrastructure resilience. Techniques to model and analyze time series data. A significant focus is placed on noise modeling. The data collected through these geodetic instruments often contains noise from various sources, including atmospheric conditions and instrument errors. To ensure accuracy, scientists need to model and filter out this noise. This enables the reliable detection of meaningful geophysical signals like tectonic movements or seasonal changes. Recent studies have employed methods like machine learning and stochastic noise modeling to improve the analysis of geodetic data, ensuring more precise results. These methods are particularly helpful in monitoring droughts, landslides, and flooding. Applications for natural hazards and climate change. Monitoring natural hazards like landslides, volcanic eruptions, and coastal flooding is one of the most practical applications of geodetic time series data. By analyzing ground movements and sea level rise, scientists can issue early warnings, potentially saving lives and preventing property damage. In relation to climate change, geodetic technologies help monitor phenomena like glacial melting, groundwater depletion, and sea level rise. Accurate data on these changes is vital for shaping climate policy, disaster preparedness, and resilience planning. Global and local scale integration. The journal underscores the importance of combining satellite data with ground-based measurements to provide a comprehensive view of Earth's dynamic processes. This integrated approach allows for monitoring both local and global phenomena, such as drought patterns in specific regions or global sea level trends. The integration of data from various sources provides a more detailed picture of seasonal variations, climate anomalies, and tectonic activities, helping scientists model and predict environmental changes more accurately. Geology and geodetic engineering are closely linked, as geodetic engineering provides the necessary tools and techniques to measure and monitor the Earth's movements, which are often influenced by geological processes. Here's how this study of geodesy is relevant to geodetic engineering. Geodetic measurements for geologic monitoring. Geodetic engineering involves the measurement, representation, and analysis of Earth's physical features. It plays a crucial role in geological studies by providing precise data on Earth's movements, faults, tectonic shifts, earthquake, subsidence, and landslides. Tools like GNSS and INSAR are central to geodetic engineering, allowing engineers to measure small-scale ground deformations and analyze the stability of the Earth's crust, which are fundamental for understanding geological phenomena. Environmental hazards and disaster management. As geodetic engineers use their expertise to monitor landslides, volcanic activity, and sea level rise, they provide geologists with essential data on potential natural hazards. This combined information enables more accurate hazard mapping, leading to better disaster preparedness and mitigation strategies. Climate change monitoring. Geodetic engineers contribute significantly to the study of climate change, particularly with tools that measure sea level rises, glacial movements, and groundwater depletion. These changes are essential geological processes that have direct consequences for environmental planning and urban development. Geodetic engineering supports these studies by providing high-precision measurements, and long-term data collection, which are essential for understanding and adapting to climate change impacts. Infrastructure and civil engineering. Geodetic engineering techniques are crucial in civil engineering projects, where the stability of the land is vital. Accurate measurements of subsidence, soil deformation, and earth movements help geologists and engineers design foundations that can withstand geological pressures. Geodetic data ensures that large-scale infrastructure projects such as bridges, dams, and highways are built safely in areas prone to natural hazards. This research journal emphasizes the synergy between geology and geodetic engineering, highlighting how advanced geodetic technologies are used to monitor Earth's dynamic processes and environmental changes. The integration of these measurements not only advances the field of earth science but also provides vital information for practical applications in disaster management, climate change mitigation, and infrastructure planning. Geodetic engineers using tools like GNSS and INSAR provide essential data for monitoring geological phenomena and addressing the challenges of a changing environment.